Hi everyone, this is Mrs. G.A. and today we're going to be modeling with exponential functions. So I have a warm-up for you guys to start, so please pause the video and give it a try, and when you're ready to check, go ahead and hit play. Alright, so here you can see I completed the t-chart for f of x equals 2 to the power of x. Then I asked you to look for the pattern you notice with the y values. So hopefully you notice that for each consecutive y value, you can find it by multiplying by 2. So there's actually that common ratio. So the y values actually kind of simulate a geometric sequence. So we're going to be using this fact today when we're testing to see if something is an exponential function. Okay, so let's see if we can use what we figured out from the warm-up to test to see if the following set of coordinates represents exponential function. So here again we have our x and y values, and we're going to try to see if our y values have a common ratio, meaning that we're multiplying by the same thing every time, times r, times r, times r, times r. And it should be the same for all of them. We do need to check as many of the coordinates as we are given. So I know for this one we can see pretty easily, oh, 1 times 4 is 4. 4 times 4 is 16. 16 times 4 is 64. 64 times 4 is 256. So this does have a common ratio. But imagine it wasn't as easy to tell what that common ratio is and you're checking. A way to check is you do the second term divided by the first term. And then you do the third term divided by the second term. So you're kind of working your way backwards to check for the common ratio. So let's go through that process. So we would do f of 1 divided by f of 0. Again, so this term divided by this one. So f of 1 is 4. And the term before it, f of 0, is 1. So that gives us an r value of 1. So we're working our way backwards to figure out what that common ratio was. Okay, now let's check the next one. So we'd have to do f of 2 divided by f of 1. So you do the y value divided by the y value before it. So f of 2 is 16, f of 1 is 4, and that gives us 4. Okay, let's check f of 3 divided by f of 2. You do need to check all of them. So 64 divided by 16 is 4. So we have another common ratio. And then last, f of 4 divided by f of 3. So 256 divided by 64 is also 4. So since all of these have that common ratio that is the same, 4, we would say yes, this data does represent an exponential function. So let's try another one together. So again, we do need to check all of them, or check as far as we can, although once we do find an inconsistency, we can stop. So here, we'll try f of 1 divided by f of 0 to see what that first ratio is going here. So again, we kind of work our way backwards. So f of 1 is 7, f of 0 is 1, so it gives us 7. Now let's do f of 2 divided by the term before, f of 1. So f of 2 is 13, and f of 1 is 7. So 13 divided by 7 is not 7. It's approximately 1.9. So since the common ratios are not the same, we can tell already that no, this does not represent an exponential function. Again, because the ratio going from here to here does not match the ratio going from here to here. So as soon as you notice that they are different, we can stop because we know that it is not exponential. Alright, so go ahead and pause the video and see if you can determine whether or not this set of coordinates represents an exponential function. And we'll check your answer in just a few seconds. Alright, so here, just by checking the first two ratios, so f of 1 over f of 0 is 4, f of 2 over f of 1 is 3.25, we can see that it already does not have that common ratio, so this does not represent an exponential function. Alright, I have another one for you to try, so please pause the video and give it a go, and hit play when you're ready to check. Alright, so here you can see that I've tested all 4 of the common ratios. You do need to check all of them, so make sure you've gone through the entire process, because maybe that last one doesn't match, so you do need to check all of them. But you do get that common ratio of 0.25, so it is an exponential function. And this one is actually an exponential decay function. Alright, so now the last thing we're going to do in this video is we're going to talk about how we can actually work with some data sometimes that is not exactly an exponential function, but is close enough to an exponential function that we can actually create a pretty decent model that we can use to help us generalize and estimate other points. So we're going to be roughly fitting an exponential function to data. So if you look at this data and you tested it, this would not be exponential. So you could check for that common ratio, it would not exist. And if you look at the points, these are the points that have been plotted, it doesn't make that nice smooth line that we would expect. But you can see that it does kind of go through, or it does kind of form the general shape of an exponential function. So since it's close enough, we can actually create a model that fits pretty roughly to this data, and then again, we can use that model to help us predict other points. So here's how we're going to do this. We're going to be using the general function f of x equals a times b, some base, to the power of x. So our job is to find a and b. So the first thing you're going to want to do is find that a value, which is our, we can say, our initial point, or we can say this is when x equals 0. So if you look at the data and it looks like this value is a pretty decent value for your function, you can use it. So we'll say that, well, when x equals 0, we can see that y is 7, so that can be our a value. So we'll start with this, f of x equals 7 times b to the power of x. Now we still need to find b. And to do that, you're going to look at the data, and it does help to kind of sketch this line through it. And you're going to do your best to pick a point that you think would represent this line. So I see one point that my line just happened to go through. Again, it depends how you draw your line. Your answer might be slightly different than mine. So we're already using this point right here. And I think that this point, to me, it just looks like a good point to use. It looks like it's kind of roughly in the middle of the other points, and it would be a good representation of this exponential function. So let's see if we could figure out which one this point is. So I can see this point would be 15, 30. So we're going to use this point temporarily. We're going to substitute x with 15 and y with 30. So we're going to substitute it here and here, and we're going to use that to help us find our b value. So we can say 30 equals 7 times b to the power of 15. So now we just need to solve for b. So we'll start by dividing both sides by 7. So 30 over 7 equals b to the power of 15. And remember, when we're solving an equation with a power, we are going to take the root of both sides. So since this is b to the power of 15, we're going to take the 15th root of each side, which sounds kind of silly, but it will do the trick for us. So the 15th root of 30 over 7, which we can plug into our calculator, should be our b value. So let's get that b value really quick. And we get a b value of approximately 1.1 if I round it. So now we know the b value. We've already determined what we will use as our a value. So our function, f of x, would be f of x equals a, again, which is 7 times 1.1 to the power of x. So this model would actually be a pretty good representation of the data we see in this chart, and we could use this model to predict other points. We could say, well, what happens if x is 25? We could use this model and we would get a pretty good guess as to what that point would be. Now again, maybe you don't want to use this point. Maybe to you, maybe this point looked a little bit better. So let's try it again, but we'll use that same initial point, but maybe again to you, this point looked better. So let's do the same thing, but we're going to use the point 1835. And again, it is up to you to, what you decide is the best, or are the best 2 points to use. So again, we still have that initial point at 0, 7. So that's our a value, 7 times b to the power of x. And we still need to find that b value. So we're going to temporarily substitute x with 18 and our y value with 35. So we'll do 35 equals 7 times b to the power of 18. Start by dividing both sides by 7. So 5 equals b to the power of 18. So again, for here to solve an equation with a power, we take the root of both sides to match the exponent. So we take the 18th root of both sides. And we'll just do the positive because we're just creating a single function equals b. And if you plug this into your calculator and you round to the nearest tenth, you actually get the same exact b value. You would still get a b value of 1.1, which would give you the same formula. So even though we used a slightly different point, it wasn't quite on the same line that I initially drew, we still ended up with the same function. Now maybe you pick a different point and your function is slightly different. Like maybe your b value is 1.2 or just maybe like maybe even 1.3 would be fine. So again, it depends which point you use. But you should get something very similar no matter which 2 points you use. Now, if you had a graph, there was maybe a coordinate on your graph that was like way out here. That's clearly an outlier from the rest of your group. Don't pick this point. Try to pick points that seem to be along the function that you're trying to create. But you can see again, we did this with 2 different points. The first time we used 1530 and the second time we used 1835, and we still ended up with the same model. So again, it is an estimate, but doing this does give us a pretty good guess of what's happening with this data. All right, so that is all for today's video. Thank you guys for watching.